Imagine a lock, not the kind on a door, the invisible lock on your bank login, on hospital records, on classified networks. For decades we've trusted it because the math behind it is brutally hard for ordinary computers. And on screen, you're already seeing the reason this conversation exists. The classical bit versus the quantum qubit. Quantum computing isn't faster computers. It's a different kind of machine, one that, in principle, could one day make some of today's most common public key encryption, like RSA, much easier to break. As of January 8, 2026, that future isn't here yet. Nobody is cracking the internet in seconds. But the hardware and the error correction results are moving fast enough that security teams have to plan as if a capable machine will arrive later. And stolen data can be cracked retroactively. And this is where roadmaps matter. IBM has said it expects the first cases of verified quantum advantage, the kind the broader community can confirm, by the end of 2026. On screen, you're looking at the kind of cryogenic system that makes this all possible. I'm joined today by a quantum hardware engineer who's watching this from the lab bench. We're going to separate the hype from the hardware and figure out what 2026 really means. Welcome to the show.
Thanks for having me. It's a fascinating and very humbling time to be in the lab.
Before we talk breakthroughs, let's ground the basics. We hear quantum everywhere. In plain English, what's the fundamental difference between the computer I'm using to record this and a quantum machine?
Your laptop runs on bits, tiny switches that are either 0 or 1. A quantum computer uses qubits. And physically, what you're looking at on screen here, those pattern circuits, are the kind of structures that can behave quantum mechanically when they're isolated and cooled.
And a qubit is what exactly?
A qubit is a controllable quantum system that can be in a blend of 0 and 1. We call that superposition. The important caveat is, when you measure it, you still get a single ordinary result, 0 or 1.
Okay, so it's doing two things at once.
That's the tempting shortcut, but it's not quite right. The power comes from interference. You choreograph the system so wrong paths cancel out and right paths add up. It's not universal parallel speed. It's advantage on specific problem types. And that maze on screen is a good metaphor. Just remember, the quantum trick isn't trying every corridor. It's shaping a wave so it statistically lands where you want.
So if the theory is solid, why don't I have a quantum iPhone yet? What's the catch?
The catch is noise. Qubits are fragile. Tiny heat leaks, stray electromagnetic fields, imperfect control pulses, everything tries to knock them out of their quantum state. And one big correction to the usual headline: raw qubit counts aren't the story. Some platforms can assemble very large numbers of physical qubits or atoms, while others focus on fewer qubits with much lower error. What matters is whether the system can run deep circuits accurately, and eventually, whether it can create stable, logical qubits.
So you can have a lot of qubits, but they're unreliable?
Exactly. We distinguish between physical qubits, the hardware count, and logical qubits, which are error-corrected qubits. On the graphic you're seeing, that's the idea. Many noisy qubits get grouped into a structure that can detect and correct errors. Depending on error rates and the code you use, it can take hundreds to thousands of physical qubits to make one logical qubit you actually trust.
But we did see movement on that recently, right? I read something about Princeton extending how long these things can last.
We did. In late 2025, a Princeton team reported a superconducting qubit design with coherence times over a millisecond, roughly 3 times longer than previous best-in-lab reports, and far longer than what's typical in many large-scale processors. And if you're watching the visual, this is what longer coherence means in practice. One signal decays quickly, the other stays intact longer. Every extra slice of time gives you more operations before errors overwhelm you. Now, the other big turning point, especially for the "can this ever scale" question, came from Google Quantum AI's Willow processors, published in Nature at the turn of 2024 into 2025.
I saw the headlines, but break it down. What did Willow actually do?
They demonstrated a surface code memory operating below the error correction threshold. In plain terms, as they scaled the code up, the logical error rate went down in the way theory predicts.
So adding more qubits finally made the computer better, not worse.
For that specific task, yes. And that's why the field cared so much. It's evidence that fault-tolerant scaling is an engineering road, not a physics dead end. But it's also important to be precise. This was an error-corrected memory experiment, not "we can run any useful algorithm now." The frontier is turning that kind of stability into full computations, with fast, reliable classical decoding alongside the quantum chip.
So how do you know a claim like that is real? If a quantum computer solves something a classical computer can't, how do you check the answer?
Verification is a whole discipline. Sometimes you use problems with built-in checks. Sometimes you validate on smaller instances where classical simulation is still possible. Sometimes you use statistical fingerprints, benchmarks that are hard to fake without the right quantum behavior. And the community is getting more rigorous about this. For example, IBM has talked publicly about verified quantum advantage as something the broader community should confirm, and they've supported community-led tracking efforts to keep claims comparable and testable.
That's infrastructure. But let's talk application. You mentioned simulating molecules earlier. Are we actually doing that, or is it still just a promise?
It's real work, but it's early. Where quantum computers look most promising near-term is in chemistry and materials, and in certain optimization or sampling tasks, often in hybrid workflows where a classical computer does most of the heavy lifting. In biotech, people are also experimenting with metabolic models, network-style representations of how cells move energy and materials around. You'll see that as a systems diagram on screen. The honest summary is, it's more pilot projects than breakthroughs, but the tool chain is getting sharper.
Metabolic modeling, so understanding how cells process energy?
Right, mapping the network of reactions and constraints. Today, quantum devices aren't simulating whole cells end-to-end, but they can be explored as accelerators for sub-problems, certain chemistry calculations, or specific optimization pieces inside bigger biological models.
And looking at 2026, I keep seeing DARPA show up in quantum roadmaps. What's their angle right now?
DARPA is pushing measurement and accountability. A big example is the Quantum Benchmarking Initiative, meant to rigorously validate approaches to building a large-scale, fault-tolerant quantum computer on a defined timeline. And stepping back, they're also implicitly acknowledging what your on-screen graphic shows. There isn't one perfect qubit. Superconducting qubits, trapped ions, neutral atoms, photonics, each has trade-offs. Hybrid architectures and modular systems are a serious line of thinking.
Like a hybrid car, using gas and electric.
That's a fair analogy. You might use one technology for fast, local operations, another for networking or memory, and stitch them together. It's hard, but so is betting everything on a single approach.
So we have progress in error correction. IBM talking about verified advantage by the end of 2026, and DARPA demanding benchmarks. It feels like the industry is maturing quickly.
It is. The conversation is shifting from "does quantum work" to "what can we verify and what can we integrate?"
Let's follow the money, because that's usually a good signal. On screen, you're seeing that curve. More capital, bigger rounds, and more pressure to show results.
The headline is, "Investment is meaningful, but it's not a straight line." McKinsey's tracking put quantum technology startup funding in 2024 at roughly $2 billion globally, and 2025 has featured some very large headline rounds. Governments are also putting real money behind this because the stakes are economic and geopolitical, not just academic.
So it's not just more dollars, it's bigger bets on fewer teams.
Exactly. Investors are looking for credible paths to systems that can run deeper circuits, show reliable error correction, and deliver narrow, defensible wins. And if you want an example of how analysts talk about timelines, Bank of America research, as reported in financial press, has suggested today's quantum computing revenues are in the hundreds of millions of dollars and could reach the low single-digit billions by around 2030. Those numbers come with huge uncertainty, but they signal this is becoming a real market.
And looking further out, McKinsey is throwing around the T word.
Right, but it's important what the T refers to. McKinsey has estimated that the value at stake from quantum computing in early impact industries could be on the order of $1 trillion by 2035, even if the direct market revenue is much smaller. In their 2025 Quantum Technology Monitor, they also project quantum technology revenues in the tens of billions by 2035, with quantum computing as the largest slice.
So for listeners who aren't venture capitalists, maybe they work in IT or security, what does this mean for their careers? If this tech keeps improving through 2026, what should they be doing?
The immediate impact is security planning. A large, fault-tolerant quantum computer would threaten widely used public key cryptography, RSA, and related schemes. The good news is we're not waiting for a crisis. In 2024, NIST finalized its first post-quantum cryptography standards. That's the starting gun for migration. Inventory where you use vulnerable crypto, build crypto agility, and start rolling in post-quantum options, often alongside existing algorithms.
Is that a hiring sector right now?
Yes, because migration is a long project. Organizations need people who understand PKI, TLS, key management, and how to upgrade systems without breaking everything. If you're in cybersecurity, post-quantum readiness is less about memorizing a new algorithm and more about engineering, where keys live, how certificates rotate, what legacy systems can't change, and how you run a phased, testable rollout.
Harvest now, decrypt later, right? Steal the data today, crack it when the machines arrive.
Exactly. For anything with a long shelf life, medical data, state secrets, corporate IP, the threat is retroactive. That's why teams are acting now, even while the most capable quantum machines are still in the future.
Sobering, but also kind of thrilling. We're watching a new kind of engine get built in real time.
We are. I'd frame 2026 as a year of sharper verification and faster engineering. Not the moment everything flips overnight, but a year where the roadmaps get tested in public.
We'll be watching closely. Thank you for walking us through the quantum leap.
My pleasure.
That's it for this episode. If your job touches encryption, start with an inventory and a plan, because swapping cryptography across real systems takes years, not weeks. We'll catch you next time.